Testing 1 2 3. All right. So again, my name is E.J. Daigle, Dean of Robotics and Manufacturing here at Dunwoody College. And in preparation for working with AC induction motors in the PLC lab, I've created this short video to talk about how we utilize the motor starter in the PLC lab. All right, so first off, when we look at our particular PLC lab, you'll see down in the bottom right corner here, you guys are familiar, this is going to be our disconnect up here. This is where our 240 volts three-phase power comes into the lab. It has a disconnect switch on the side, and that's also where we do our lockout and tagout. It's also where our L1, L2, and L3 power is going to be available for the power circuit for our three-phase motor. So that's an important thing to note as we start to work with this particular circuit. So first off, when we talk about AC induction motors typically are going to use a higher voltage and a higher current than other AC devices. So up till now, most of the AC devices we might have worked with in the lab, we might have worked with an AC fan, we might have worked with some AC indicators. We've worked with a lot of DCIO at this point. This will be our first experience working with some of our higher voltage. In our particular case, a 240 volt AC induction motor. Typical AC motor like those in our lab operate on 240 volts AC three-phase power with a normal operating current of approximately 1 amp. So anytime you're looking at one of these motors, you can always look at the nameplate on the side of the motor to see exactly what it is that you're dealing with. And you can also look at on the motor nameplate itself, it may have some wiring diagrams there too for if you're going to wire high or low voltage or wire delta. In some cases you may even have to take a cover plate off to look at that. Before you do any of that stuff though, I can't say enough as far as safety is concerned when dealing with 240 volts AC. Make sure as you're doing all your wiring that you are locked out and tagged out. I even recommend grabbing a meter and just testing for voltages to make sure there's nothing that could cause us any trouble. Now, why do we have motor starters? Well, a couple of reasons why. Typically, when we deal with AC induction motors, not only are we dealing with a high voltage, a higher current, but we are also dealing with a very expensive device. So an AC induction motor could cost upwards of several hundred to even several $1,000s for a good motor. And if we were to allow a overload condition to exist, we would prefer not to burn up the motor and maybe burn up a set of heaters or a set of overloads or a fuse or circuit breaker, something that either can be reset or something that might cost, consider, $1 to replace instead of several $100s to replace the motor. One of the things to think of as you start up a motor, kind of like if you're pushing a box across the floor, if you start pushing a box, it takes more energy for you to get that box moving than it does to keep the box moving. From the case of the box, that's called the coefficient of friction. Once we get it moving, we've got that momentum now, we can keep it moving. It's similar with an AC induction motor. It's going to take more energy to get the rotor turning inside the stator than to keep it turning inside the stator. We call this condition inrush current. So it occurs when an AC induction motor is first turned on and no magnetic field exists. Typically it can be 6 to 10 times that of the operating current. So even though you might look and see on the nameplate that this is a 1 amp motor, it is worth noting that that's the normal operating current. That is not necessarily the 6 to 10 times startup current that it's going to take to get that motor turning. All right, so what does this motor starter do? So the motor starter is very, very similar to a relay. To be completely honest with you, this upper part that we call the contactor, if I take the overload off of this contactor, it really essentially is just a relay. And it might look similar to the master control relay that we use in the lab for isolating power with our emergency stop and so on and so forth. So that's an interesting point. You'll see, let me go back here. You'll see this little magnetic contact will pop in and out as we energize the coil. And some of these will be the coil, some of these L1, L2, L3. There may be an auxiliary contact in there as well. The big difference though, when we talk about what's the big difference between a motor starter and a relay, Well, motor starter has two parts. It has the contactor, and it also has this this overload protection on the bottom. So the overload protection in older days or in bigger motors, they actually were heaters, and sometimes they were things like bimetallic strips that would heat up and break apart as the current would heat up. The two metals would heat up at different rates, and they would pop loose, and you'd have to reset them in the case of a bimetallic strip. Or in the case, we even had things like solder pots that the solder would melt and break the circuit. More common nowadays is, especially for not huge motors, you're probably going to see a lot of what I would call electronic overloads. What that means is they may have set points. Some of these different things that you see down here may be set points that I can do on the overload itself. So I might be able to set a time delay. I also might be able to set the current at which I want it to trip. So it might be that because of that 6 to 10 amps of startup current, I'll set this to, let's say, 6 amps of current, but I'm going to have a time delay of 1 second or 2 seconds. So it's allowed to go over current for a little bit before it trips, to kind of take into account things like inrush currents or spikes. But I can also set it low, and I can set the time delay low. So if it's a very expensive motor or a very important motor, I can't find a replacement readily, I may set this lower knowing that it'll trip out, but that I am completely protected. All right, so as you look at the actual motor starter here, if you take a look at the motor starter itself, your contactor portion up here, you'll see up at the very top here on the right, let me get here. This is A1 and this is A2, but because we're actually passing through to the contactor, A2 is actually down here. So A1 and A2 represent the coil. Just like the coil on a relay, A1 and A2, if I can energize A1 and A2, the contactor is going to click in, and you'll see that magnetic contact click in. L1, L2, L3, so this part right here, L1, L2, L3 is here, here, and here. L1, L2, L3 is your motor supply voltage. This is the voltage I'm going to supply. So for us, that's going to be your 240 volts three-phase, your lines 1, 2, and 3. Down on the bottom down here, you'll see T1, T2, and T3. And T1, T2, and T3, that's what you're going to wire up to your actual motor. So I'm passing L1, L2, L3 through the contactor, through the overload, and down to the motor to turn on the motor. 13 and 14 is what we call an auxiliary contact. So you'll see 13 right here. And let me see where he is down here. 14 is way down here. 13 and 14 is your aux contact. In the case of a non-PLC application, we could use this as a holding contact, to use a momentary start push button and put it in parallel with that to create a holding contact. The aux contact could also even be used for something like a green pilot light. If I wanted to have a light on whenever the contactor was on to show that something is working. All right, 95 and 96. This is your normally closed overload protection. Okay, this would allow me to use this as a break contact. So if an overload condition ever occurred, it would open up with the overload and it could break my holding circuit. 97, 98, that's going to be my normally open. That's these guys right here. That's my normally open overload contact. So maybe I want to have a light up, a red light or something to display that there's been an overload condition. And until I reset it, that normally open contact's closed and the normally closed contact is open, signifying that there's both an overload condition and also hopefully breaking that circuit. Some interesting notes on contact nomenclature. If we look back here, we'll see 95 and 96 and we see NC. It's kind of interesting to look at that. 95, 96, when we're talking about contact pairs, 95, 96 is always, well, I shouldn't say always, but it's typically associated with a normally closed overload contact. 97 and 98 is typically associated with a normally open overload contact. However, on auxiliary contacts and other contacts, contact pairs with 1s and 2s are typically going to be normally closed contact pairs. Contact pairs with 3s and 4s, such as 23, 24, 33, 34, or 13, 14, those contact pairs are typically normally open. So if I go back to here, the one that we could look at would be my 13 and my 14. And I can see my 13 and 14 are my normally open auxiliary contact. And we said, oh yeah, 13 and 14, I'm expecting that to be a normally open contact. But you can also see down here on your overload that it actually signifies this guy as a 22 also. I think that's a 22 down there. Let's see here. No, let's see. Could be a 23. Hard to see what that is down there. In our case, though, we're worried about the 13 and 14 is what we're really worried about. All right. Without a PLC, if we're actually going to look at wiring up a motor starter without a PLC, this is the way we'd go about doing it. This M1 represents my coil. So in our case, this was A1 and A2 on my coil. Typically what I would do if I wasn't using PLC is I'd have my 240 volts, 3-phase power, and I would tap off 2 of those phases. And now I have 240 volts single phase. So this is 240 volts and it's single phase is what it is. And then I go through a control transformer, and on this side I would get my 120 single phase. So what I've done is I've created a low voltage circuit for control. The reason why is when I press start and I press stop, I'm routing that 120 through the circuit. And I'd prefer not to be routing 240 or 480 through a push button that I'm pressing. You can imagine this kind of like the key switch on your car. The key switch on your car, that key switch routes a low current and a low voltage to your starter solenoid, which is essentially just a relay in your car. And then that starter solenoid is what that is actually going to run the hundreds of amps current down to your starter. So we don't run hundreds of amps of current through the key switch that you're grabbing on the steering column of your car. Instead, what we do is we run a low voltage, low current through the key switch, and that key switch goes to a coil that then triggers a contact that runs hundreds of amps current down to your starter. Same thing here. In this case, when I press the start push button, I'm energizing this coil. So when I press start, the coil energizes. That coil energizing closes the normally open contact. I can release start now, and now that normally open contact is going to hold it. As soon as M1 energizes, not only did this auxiliary contact close holding the circuit, but now each one of these power contacts closed as well on the contactor. And what that did was that routed the 240 volts 3-phase down to the motor and actually energized my 240 volts motor. So in this case, I've got a 120 volt control circuit that is driving my 240 volt power circuit. And that's very, very common, whether it be in your car with a low current signal triggering your starter, or it could be a push button in a relay in another application, or a motor starter in this application. And it's also worth noting that it's not uncommon for a motor starter to even have a DC coil. That's not an uncommon thing at all. So that control circuit here, we can see the 120 volt control circuit. Now what we didn't include in here was the 95-96 contact. So if I hit start and M1 energizes, I also have some overloads inside this motor starter over here, and those overloads can trip out my holding circuit. So what I would do is I would typically put that 95-96 contact right here, and that way either pressing the stop or the overload contact opening would allow me to trip us out and actually take out my coil, which would de-energize the holding contact, and it would de-energize my power circuit. So all we're doing there is we're kind of showing where that 95-96 contact could be placed in our circuit here. So without a PLC, again, we're just talking about using only a motor starter in all of these applications. This is motor starter only, no PLC. And then our power circuit is over here, and we already kind of talked about this, but when I energize this start push button and M1 energizes, this closes, but so do these, which actually route my 240 volts down to the motor. All right, with the PLC, when you do this in the lab, you're actually going to see 3 I/O listing sheets. The I/O listing sheet's not the best example of how to use a motor starter from the case of like the power circuit for the motor starter, but since we use it for all of our PLC I/O, we just use the same sheet for the power circuit. The first I/O listing sheet you're going to see in the lab is going to be something you've been used to seeing. So in this case, I've got my PLC-IO, so this would be probably my input module, right? And this would probably be my let's say my output module. Okay, and I don't know what these are being used for, but I can see I got a start, I got a stop. That potentially could energize my my motor via another output module. I've got some proximity sensors here and here. I've also got my DC output module that's going to energize some lamps. So maybe I can have a green lamp for run, a red lamp for stop, and maybe the yellow lamp signifies some sort of other condition. So that's my 24 volt DC. You're used to seeing this sheet. This is a sheet you've been wiring up for weeks now. Now, when we haven't been working, well, we've been working a little bit with the 120 sheet. On the 120 sheet, I've got 120 volts AC in neutral, single phase now. You'll see I'm bringing power into the PLC. And I also have my return for the PLC, and then I have my ground. So all this guy's doing is this is just powering up the PLC. I've got 120 volt power required to bring up my SLC 500 PLC. And now what we're doing here is we're using the relay output module. So I don't know where it is positioned in your rack necessarily. I could be in slot 3 or 4. But what you'll see is we're routing 120 into the relay contact VAC VDC. So we're supplying the relay with 120 volts AC, and then the output of the relay, out 0, is going to go to the motor starter, A1 and A2, and back to neutral. So because we're routing 120, this will be a black wire, this will be a black wire, and on the other side of my coil will be my white wire. And so now we've actually energized that motor starter coil, which then will close the contacts that route the power down to the motor starter. And now I've got a 240 volt AC power circuit. On the 240 volt AC power circuit, I did this a little funky, but you'll see I've got an L1, I've got an L3, and I've got an L2. So what I've done is I've supplied power to the motor starter. So this is the power circuit now. So the motor starter L1, L2, L3 needs power coming in. L1, L2, L3. Remember where that is on the motor starter itself. That L1, L2, L3 is up here. L1, L2, and L3. So I'm going to supply power to the motor starter. And then coming out of the motor starter, I have T1, T2, and T3. And the way we're wired up in the lab is our 3 motor leads come up to the job board on M1, M2, M3. So I will need to run T1, T2, T3 to M1, T2 to M2, and T3 to M3. And so what happens then, so let's look at where T1, T2, T3 are. T1 is down here, T2 is down here, and T3 is down here. So now what's going to happen is whatever code I write to turn on this coil, when you know the start stop, whatever it is inside the PLC code, is going to turn on that coil. And when that coil turns on, I'm going to make a connection from L1 to T1. So basically, as you look at that motor starter, what's coming into L1 is going to get routed out of T1. What's coming into L2 is going to get routed out of T2. What's coming into L3 is going to get routed out of T3, and it's going to go down to your motor. So if I have 240 volts coming in, that's what's going to go out. Now I want to bring up one kind of side point here before we get rid of this thing completely here. One of the interesting things about a motor starter, let's see if I can just find a nice little blank page, is you can also do 2 motor starters if you want. So let's say I have a motor starter here, right? And it's L1, L2, L3, T1, T2, T3, and these are going down to my motor here, right? I've got M1, M2, and M3. And so in this case, M1, M2, M3, and so this is L1, L2, and L3 coming in. Now let me see if I can figure out how to change my pointer. Pointer options. I want to go to a different color here. So what I could do is I could call this my forward motor starter, right? So if I run L1, L2, L3 down to T1, T2, T3 down to M1, M2, M3, I run in forward. However, I could switch it up. I could also have a reverse motor starter. And I could have L1, L2, L3, and T1, T2, T3. And maybe in this case I run L2 to L1, L1 to L2, and L3 to L3. So now essentially L2 goes to M1, L1 goes to M2, and L3 goes to M3. And the thing to remember about this is switch any two phases. Switch any two phases to a three-phase motor, and you will change direction of that motor. Now this is really, really dangerous what we just did here. Why? Well, because what you would want to make sure of is you would want to make sure that you could not have these two on at the same time. So you might say, well, I can have forward, you know, but not reverse to give me forward, right? And that could energize A1, A2 on this guy. Or I could have reverse, but not forward to give me reverse, which would energize A1, A2 on this guy, would energize the coil. The reason why you wouldn't ever want these to be on the same time is essentially what you'd be doing at that point is shorting out L1 and L2. And that would be very, very bad. So not uncommon to use two motor starters to control direction. Probably more common nowadays is you'll see things like VFDs, variable frequency drives that allow you just to hook up one device, and the cost of the VFDs have come down substantially to the point that we, a lot of cases may not have to do something like this to change direction. We can just use a VFD to take care of that. But I just thought that was interesting note for you to consider as you look at all the different things that you can do with a motor starter. So hopefully that'll prepare you for using the motor starter. And when we get up to the lab, by all means, see me with any questions. Thanks.